record. So today we are going to study tangent planes and linear approximations. Okay. The idea is that you have a graph. Okay. You have a graph of a function in three-dimensional space, and you want to find the tangent plane to the graph. Right. So here is here's a picture. Okay, so given equation, then you get given function f, right? Then you get equation. There's two variables, right? And this x and y are in its domain D. Okay. So when you draw the graph of the function, is going to be a surface. The graph of the function f is the graph of the equation. This is the equation, okay, that tells you the relationship among the three variables. So if we draw the graph, it looks like that. If the function is positive, this is a domain D. It could be a square, it could be a half plane. Then if the function is positive, the z value is always positive. So where's my, I don't know what's going on here. So the phi is gone. Hey, hold on. Yeah. So you have a kind of loop above that. This is a surface. Okay, it's a surface. So, and a point on the surface. Okay, so we want to find equation for the tangent plane. This is a tangent plane. Okay, in order to find tangent plane, what do you have to do? Well, in the book, you already given the formula, right? And without any proof, okay? Well, because since we already studied we already studied how to find the cross product, right? So the idea is that if you, I'm going to find a two tangent vector, okay? Two tangent vector to the surface. The one tangent vector is going to be, so the idea is that if this is a point x naught, y naught, right? In the domain, then you have the point x naught, y naught, z naught, right? This is the point on the plane. So I have to find a normal vector, right? So if I have to find a normal vector. This is n. So if I find a normal vector, I can find the equation to the tangent plane. So the normal vector will be the cross product of two tangent vectors, because the normal vector perpendicular to all the tangent vectors to the surface. How can you get a tangent vector? The idea is that you consider the first one, consider curve on the surface. So the curve on the surface will be the first component will be t, right? And the second component is a fixed, okay? And the third one will be just f, t, and I can use x, yeah, no problem, use x. So you traditionally we use a parameter t. So this is a curve on the graph. You fixed y naught, let t changes, okay? So t, when t equals x naught, you get x naught, y naught, and the zero naught, because zero naught, x z naught is going to be fx naught, y naught, okay? So this, when t equals t naught, x naught, that passes through that point. So the derivative of this function, a vector function, right, is going to be the tangent vector to the curve. let me draw the curve. Yeah, this is a curve on the graph, and then under that is this straight line. Sorry, this is straight line. Okay. Yeah. Under that, this is the curve on the graph above this straight line. This straight line is a parallel to the x-axis. Okay. So this will be the tangent vector to that curve. Of course, this will be the tangent vector to the surface. Okay. So when you differentiate 1, 0, f, the first component is right, the partial derivative. Okay. All right. So in particular, when t equals t naught, x naught, there's going to be 1, 0, fx, and x naught, y naught. Okay. So this is going to be a tangent vector to the curve, okay, determined by gamma. Of course, it is going to be a tangent vector to the surface. Is a tangent vector to the surface, okay, to the graph. Okay, this is also called the graph at the point, at that point. Okay. Now, similarly, okay, another vector 0, 1, f x naught, where partial derivative with respect to y, is a tangent vector to the graph again. Is a tangent vector, and I'm going to call it, let's call it denoted by u, as that be v. Okay, tangent vector to the surface, to the graph. Okay, at that particular point. So let me draw the picture right now. Here's two vectors. That's a u, and here's a v. Okay, so two vectors tangent to the surface. Then this will be the normal vector. So m is perpendicular to the graph. Okay, at that particular point. Okay, let's find out what is n. Okay, so n is going to be list I, j, k, and here's 1, 0, f, x, and 0, 1, f, y. Okay, so you expand it. This is a cross product, right? So for the first term, look at this push. It is going to be, I think, determinant, right? And that's going to be negative f x naught y naught. Okay, I, then minus, I think it's negative. Yeah, I can look at this, and j, and plus, okay. Okay. So I find this a normal vector. So here's a important fact. This is not necessarily has a unit length. So you get fx, given the graph, this is always perpendicular to is a normal vector. To the graph. Once you get a normal vector, you can get tangent equation for a tangent line. Normal vector to the graph of f at the point, at this point, okay? Where, of course, z naught is going to be determined by this equation. Okay. So this is once you get this, then the equation for the tangent plane is easy to get. Okay, it's easy to get the equation for the tangent plane. How do I do that? Here's a plane. Here's a surface. Now we forget the surface. We just look at the plane. Okay, this is a. Okay, so this is a normal vector, right? So the normal vector is perpendicular to the surface. More precisely, is perpendicular to the plane, okay? To the plane. So I can describe the plane in two different ways, okay? One is I take an arbitrary point, x, y, z, right? And then I look at the vector in the plane. So x minus x naught, y minus y naught, z minus z naught, the cross product. Now the dot product should be 0. If this is a point on the plane, if only if the vector between those two points is perpendicular to the normal vector, right, from the picture. If this is a p naught, that's a p, okay? So it's perpendicular. So if you write down the details and look at this, what is the n, right? N is going to be this, right? So I just look at the product. So what I'm going to get is the x minus x naught minus y, x0, y0, y minus y, y naught, and plus 1 times that. So this is the equation for the plane. Okay. This is the equation for the plane. Okay, so let's use that to find okay. So this is the equation for the tangent plane. It's an equation for the tangent plane. Right. All right, so let's do some exercise. I have another way to describe the plane, okay? But let's do some exercise from the book. We have the formula. I think the formula is not proved in the book, but it's okay. I explained to you already here, okay? So this is a course for engineering and the math major student, okay? Since we only have a very small number of students in math major, we don't have another special course for that. Okay, for math major students, they should know how to derive the formula for the tangent plane. Okay, I just tell you the difference. For students in engineering, they just need the formulas to apply the formulas to solve the problems. That's more difference here. Okay, but since we have to combine them into one course, that's why we have a course for science major, for math major, and engineering. Okay, so I have to explain how to get to the formula, but then in the homework assignment, you're not required to derive the formulas. Okay, you just apply the formulas to solve the problem. So let's do problem number 2 from the book. Okay, you are given this equation. Okay, find the tangent plane at the point 2, 3, 3. Okay, first of all, this is a point. Make sure this double check. Sometimes could be typos. Okay, this is a point on the tangent plane, on the plane, on the graph. So when x equals 2, y is 3. I want to make sure it's going to be 3, right? So it's going to be 4 squared minus 2 times 2 squared minus 5. 16 minus 8 minus 5, and that's going to be 3. It's indeed as this is a point. Okay. The next step is you have to find the yeah, what is f of x? F of x is x plus 2 squared minus y1 minus, right? Okay, so you have to find the partial derivative. That's our motivation why we have to find derivatives, right? So when you differentiate this function, only the first term survives. It's x plus 2. And then you find the partial derivative with respect to y. And only the second term survives. It's minus 4, y minus 1. Right? All right, so you have to evaluate at this point. So when x is 2, I get 8 here. When y is going to be 3, and minus 4, 3 minus 1, it's 2 times, it's also 8. Okay. Now, remember the equation, okay, for the, you just apply the formula. You already got the formula, right? The equation for the tangent line is given by, this is just an equation for the tangent line, right? This is going to be negative, okay, 8, x minus 2. No, this is a negative, yeah. Remember, this is a negative fx. Negative fy is a positive, y minus 3, and plus z minus 3 equals 0, okay? Why this positive 8? Because look at this formula here. This is a, okay? In the book, they move all the terms to the right-hand side, okay? Another version of the tangent equation is going to be z minus 0 equals fx x minus x0 plus right. That's the general formula, right? And you can also move z naught to the right hand side, okay? You can also move z naught to the right hand side. Z naught is going to be it's going to be written as in that form, okay? So there are many ways to describe the equation for the tangent line equation. So that's not unique form. Okay. All right, let's. So the tangent line can be viewed as a graph of some linear function. Okay, so the tangent plane can be viewed as the graph of some linear function. See that this is a linear function in x and y. Okay. You can you can modify, you can simplify that, but we can let's do this. Find the linear equation for the tangent line. So let's do problem number 4. Right, z equals x over y squared. Okay, and find the tangent plane at the point -4 and 2 and then -1. Okay, so if you just memorize the above formula, then you clearly just need to evaluate, yeah. You know, here, yeah, evaluate the derivative, right? It's when x is -4, y naught is going to be 2, right? I'm pretty sure z naught is going to be -1. But you can plug them into the formula. It's going to be 2 squared, which is -1. It's guaranteed. Otherwise, this is not going to be the point on the graph. All right. Yeah. So So the function here in x, y is x squared over y squared, right? So now we have to find the partial derivatives in order to find the equation for the tangent line. So I just find the partial derivative, right? It is going to be 1 over y squared, right? Fy, x and y is going to be, when you differential 1 over y squared is going to be negative 2x y cubed, okay? 2x over y cubed. Just derivative with respect, find the derivative of this function with respect to y squared. So you have y negative 2, so that's why you get a negative, right? All right, so now you have to evaluate at those 2 points. That's 1/4. And then you will get 2, negative 4, and 2 cubed, okay? So this is going to be 1. So we find all the information. So what is our equation? So the equation can be z minus z naught equals the derivative, partial derivative of f with respect to x, and x minus negative 4 plus 1 x minus 2, now y minus 2, okay? So this is the equation. Yeah, this is a z naught, this is a partial derivative, that's partial derivative, right? So simplify. X plus 4 and the y minus 2. We can continue simplifying. I can get, so I get quarter of x plus y minus 1. I can also move 1 to the over to the right hand side. Okay, it's minus 2. So z equals quarter of x plus y minus 2 is an equation. This is a linear equation, right? So it's a linear function. If you denote this by g, x, y, right? So the tangent plane is actually going to be graph of this linear equation. At the point negative 4, 2, right? And the negative 1 is the graph of another function, of the linear function. Yeah, the linear function is given by a quarter of x plus y minus 2. So linear function is simpler, okay? Than general function. Now, let's look at the picture, okay? You see, the original function is very, it's not a linear function. It's a 1 or x over y squared. So the graph, it's harder to draw it. Let's draw the graph. Where is the negative 4? Negative 4 is here. 1, go back, right? And the 2 is on this side. Negative 1 is, so this is a point. You go down by 1, okay? So the graph, yeah, this is a point P, negative 4 and 2, negative 1. So it's harder to draw the graph. I just draw the graph like that, okay? Sketch the graph. It is harder to draw it, okay? Now, the tangent plane, okay? This is a tangent plane. It is a graph of another linear function. What does that mean? Since the tangent plane is a plane which touches the graph at that particular point, and this is a closed plane to the graph. So if you look at an arbitrary point here, and look at an arbitrary point here, which is close to, this is just a 0, okay, on the plane, okay, for an x, y, close to -4 and 2, okay? The gap between those 2 points, this is a gap, okay, between those 2 graphs is small, okay? The gap between the 2 graphs, okay, is small, okay? What does that mean? That means the value, i.e. the difference, so in the z coordinate, they have the same x coordinate, right? So the difference of between the z coordinate is small. Z coordinate, okay, at the point x and y is small, okay? So if you look at the graph, okay, so now if this is a z coordinate, right, it's going to be x over y squared, okay, for the x close to -4 and 2. But this is a z coordinate, and then my another plane is -4, 4x, 1/4 x plus y minus 2. So this should be equal to g of x, y. It's going to be quarter of x plus y minus 2. Okay, so that means this strange function x over y squared, if x, y close to -4 and 2, and then x over y squared should be close to the linear function. Okay, this is the linear function, the value. Okay, if you look at the graph, and this is a graph is z equals f of x, right? And this is a z equals a quarter of x plus y minus 2. Okay, that's the equation for the tangent plane. So for the same x, right, you get 2 points. One point is on the graph of f, another point is on the graph of the tangent plane. And there's a gap between those 2 points. The gap is the difference of those 2 functions. One is a linear function, other one is a f, right? Right, so this, and then that should be smaller and smaller when x, when x, y getting close to -4 and 2. So you can use a linear function to estimate the value of the function, original function. Let's do one more problem for the tangent plane. So z equals natural log of x minus 2y. Okay. The point, yeah, find the tangent plane at the point 3, 1, 0. And then indeed, this is going to be a point. Yeah, the point, this is going to be 3, it's a 1, and you can double check. It's going to be natural log of 3 minus 2 times 1, and which is going to be natural log of 1, which is 0. Okay, indeed, this is a point on the graph of the function. All right, so the function, the formula for the function is natural log of x minus 2y, right? So you have to differentiate. You differentiate. So you get the partial derivative, right? So you get x minus 2y. Then you differentiate the inside function, right? 2x partial derivative. Let's use a partial, right? So that should be equal to 1. So that's just x minus 2y. Okay? Now you differentiate with respect to y. So first of all, you still get this. Then partial derivative of this function inside with respect to y. So that should be given 2, negative 2. So it's going to be negative 2 over x minus 2y. So you find all the partial derivatives, but you still have to evaluate at the point 3 and 1. 3 and 1, I got 1. Okay. And here's 3 and 1. Again, negative 2. Okay. Now, so you get everything, right? So you have to recall the formula for the tangent line. So that's going to be z minus 0 equals the partial derivative 1 times x minus 3 minus negative 2. Right? So that's the equation. And this is a linear equation. Okay? No, not plus 2. So, because this derivative is negative 2. Y minus 1. Okay. Yeah, look at this equation. Yeah, sorry. So the original equation is like x minus 1 plus y minus 1. Okay. So your y naught is 1, and let's check. Well, I forgot the number, right? The y naught is 1, x naught is 3. Okay. So that's why y minus 1 gets x minus 3. Minus? No, it's positive. I moved it to the one side. Yeah. Yeah. So z is equal to x minus 2y, and minus 3 last 2, so it's minus 1. So this is a linear function, okay, for the graph of the tangent, for the tangent line, okay? So I can also say that this is a z, right? This is gxy. So for x and y close to 3 and 1, so f of x, y should be close to this linear function. Okay. The reason is, you know, this is a surface, right? This is a point, and above, and here is going to be 3 and 1, right? And this is tangent plane, and here's an arbitrary point x and y, and this is above, right? So look at that, right? The z value is going to be, for the tangent plane, is going to be x minus 2y minus 1, and for the graph will be f of x. So the gap between them is going to be the difference, okay, of this function. So of these two functions. So that means yeah, this is if this is the epsilon, and then f and xy, is really close to, it can be approximated by this function. So what is the function here? Is an h log of x minus 2y, right? So it can be approximated by x minus 2y minus 1 if x is, yeah, for x and y close to the point 3 and 1, okay? At the point 3 and 1, they're equal, okay? They're all equal to 0, okay? At point 3 and 1, they're equal, okay? I should have said that. At the 3 and the 1, they're equal. They're all equal. They're actually equal to 0. Okay, both are equal to 0. Okay. So we gradually come to the part about a linear approximation of the function. Okay. So linear approximation of function is going to be this linear equation. Okay. So here's my here. Let's go over again. You know, the graph. The graph of the tangent plane is given by above equation. Okay. If I move z naught to the other side, I get a linear function. So let Lxy to be right, and we will see that f of x and y is close to ln xy. I should use L here. Yeah, as x, y close to, this means close to, close to x naught, y naught. Okay, so this ln x is going to be called a linear approximation of the function. Okay, yeah. So this L x is called this is called the linear approximation, okay, to the function f of x. You have to specify at which point at that particular point. Okay. Right. The reason we can see that from the graph. This is why it's a linear approximation. Right. And so let's take a look at the next problem. Explain why the function is differentiable at the given point and find the linear linearization of the function. Yeah, it's linear approximation linearization. Okay, it's the same word. So here's a f of x, y equals square root of x times y. Okay, find the linearization, whatever it's called. Yeah, then x, y for the function f at the point at the point 1 and 4. So this is a complicated function, right? Square root of x times y. So I want to replace it by a linear function, okay? And how do we solve this problem? Do you remember, in Math 165, we have a linearization we start linearization to of a function in one variable. So we have two variables, or more than two variables maybe. So you write down the step 1 is write down the formula, okay? And then you solve the problem. It's going to be f 1 and 4 plus f prime 1 and 4 x minus 1. And here is 1 and 4 and y minus 4. Okay? So you write down the linearization formula for the linearization. Then it's clear that what you have to do, you have to evaluate the values, 3 values. Okay? Let's find the partial derivative first. How do you find the partial derivative? Yeah. So look at this function. You can it's written in this form, right? So when you partial derivative with respect to x, you just differentiate, and then 1/2 is minus negative 1/2. Then you differentiate x times y with respect to x. X is gone, so you get a y. Okay? Then you differentiate with respect to y. You get x here, because the derivative of x times y with respect to y will be gone, x is left. All right, so now you have to evaluate all those. So it's going to be 1 times 4, which is 2. That's easy, right? And f prime 1 and 4, 1/2, 1 times 4 to the negative 1/2. What is y? Y is 4. I get 1. I get 1. Right, because the denominator is going to be 2 times 2. So 1/2, 1 times 4, and that's going to be 1. Right, so this is going to be 1/4. All right, so we find all the values. Now, if you write down clearly, step by step, and even the computation is wrong in some step, right? You get the wrong formula for the linearization, the final formula, but you still get 80% of credit because clearly, you show me how to do the problem. So you write down the formula. It's very important before you solve the problem, okay? And then the linearization is going to be, this is 2 plus 1 times x minus 1 plus 1/4 y minus 4, okay? You don't need to simplify it. This is in good form. So this is a function which really tells you and gives you a good approximation. So in other words, the function is very close to this as x, y close to 1 and 4. So I can use that to estimate. For example, what is the value of 1.01 times 4.01, right? And using this formula, I can estimate. So this is close to, okay, close to L 1.01, 4.01, okay? And when you plug into the above formula, it's easy to compute. X 1.01 minus 1 is 0.01 and plus 1/4. And this 4.01 minus 4 is going to be 0.01 again. So you can quickly get, it's almost equal to, but the addition term is pretty small, okay? I think this is going to be 2 plus 0.01 plus 0.0 and 0.25, right? So this is a number that's a very good approximation to the square root of that, the product of those two numbers. Okay. So now I'm going to introduce a new concept about so-called differential of a function. Before we do that, I needed to give a definition when a function in two variables differentiable at some point. Okay, that is actually be stronger than the existence of partial derivatives in a given function. Right, we can figure out whether the function has a partial derivatives. Yeah, that's just a reduce the problem to the one to function in one variable. Okay, so given function f, okay, defined on domain D, okay, and this is a point inside D, okay. So the partial derivative, remember, right, is defined to be f x naught plus h y naught minus. Okay, so actually we view it as one variable function, and with the second one fixed. If the limit exists, then we say the partial derivative exists, right? That's the definition. So this exists if and only if this function with the second variable fixed has derivative, differentiable, I should say, is differentiable with respect to x with respect to x. Okay, so we just reduce the problem to a problem function in one variable. Now you have two variables. How can I say a function differentiable at two variables? In two variables. So here's the definition. It's slightly different. Okay, so f is differentiable at this point if we have the following properties. If f x naught plus delta x minus, right? This is the difference, right? Sometimes it's also called the delta z, okay? This is also denoted by delta z if you denote z equals if z equals f of xy, okay? And this is going to be equal to this. Not only that, then there's a small problems here, small errors, and that is going to be epsilon 1 delta x, epsilon 2 delta y. Okay, this is a small errors. Okay, so where epsilon 1 and epsilon 2 approaches 0 as delta x delta y approaches 0 and 0. Okay, so if the function has such properties, then we say the function is differentiable at that particular point. Okay, so first of all, you have to have a partial derivatives. So a function is differentiable implies the partial derivative exists at that point, but conversely is not necessarily true. Okay, so this is a it's similar to the differentiability of the function in one variable at a particular point. Okay, so look at it. You're pretty familiar with this. So this looks like coming from the linearization something, right? So that's the definition. Okay. Now, what I want to say that f, here's a note. F is differentiable at some point implies the partial derivative exists. But does not mean conversely is not true. Okay, not true. Okay, conversely is not true. The partial derivative exists does not mean the function is differentiable, because differentiable means you have to have this kind of this kind of equations you have to have. Okay, so the arrows should be getting smaller, as delta x delta y approaches 0. So that the above condition is much stronger than just the existence of partial derivatives. But there is a theorem guarantee the function is differentiable. Okay, but we are not going to prove that here. So if fx and fy sub y exist near the point x naught y naught and continues at that point, and then you must have the above property. Then f is differentiable at. Okay, then you can prove that the above is correct. Okay, so they're not equivalent, but you can check whether the function differentiable use this theorem. Right, let's take a look at the following examples. Okay, f of x, y equals x times e to the this. Okay, I'm going to look at the point when the 0. Okay, I want to show this is differentiable. It looks nice, it's differential, but you have to use the. It's easy to find the partial derivatives, but it's harder to verify this identity. Okay, this property. So I'm not going to verify this property directly, but what I'm going to do is, well, the partial derivative is nice. That exists, that continues. That's it. All I have to do. So let me find the partial derivative. So when you differentiate, you get an x e to that, right? Plus x, then differentiate e to the xy with respect to x, I get a y. Right? That's the first thing. Then I differentiate with respect to y, I got x squared e times xy. Now, clearly, both exist nearby when the 0. Of course, we find the derivatives. So you see that they both exist, okay, everywhere, not necessarily nearby that point. Everywhere, okay, and continuous everywhere. So in particular at that point, so then this implies f is differentiable everywhere. Okay, at any point, in particular. Okay, in particular at that particular point. Okay. All right, so let's look at z. Z depends on x and y. Okay, so now you have three variables. In the above definition, stock can be written in the following form: if delta x is going to be the change in this, and delta y is going to be changing the right. Yeah, let's go back to this equation here. Look at this, right? Yes. Then delta z is going to be yeah, I'm still okay. Delta z is going to be the change in the y variable. Okay. So this is a yeah, the change in the z variable. Okay. So f is differentiable means at the point we have f is differentiable at the point x0 means delta z equals delta x, delta y, and plus those terms, right? Where epsilon 1, epsilon 2 approaches 0. Okay, so let's go back. Yeah, let's look at this. I'm going to introduce a so-called differential of two variables. Differential variable. Differential, it's hard to understand the next concept, honestly. So dx, okay, is called the differential of x. Okay. Okay. So dy is called differential of y. Okay. And if z equals f of xy, okay, then the differential z is given by, it's not arbitrary, is given by the following formula. So dz, just look at the above approximation, is going to be f x and replace delta x by dx. Okay, that's it. You don't have any extra terms. So if I ask it, if z equals f of xy, if we ask you to find differential of z, you just needed to find the partial derivatives and multiply by dx. Okay. Now this formula can be written in another way. Okay. Look at this, right? this is a partial derivative of x and y, right? Right? But f of xy is also is just a z, so you can simply like z. So f is gone. Okay, it's amazing, yeah. So now I even forget any other variables. So given quantity z, okay. If you believe it depends on another quantity x and y, since the differential of z is going to be given by the above formula. So if z depends on x and y, then the differential of z is going to be partial z with respect to x, partial z with respect to y, dy. Okay? So it's like a chain rule. It's kind of interesting. Yeah. And if we have a more than two variables, then you just keep writing on this, right? So if I have another, yeah. So if W depends on X, Y, Z, for example, a quantity W, then dW is going to be partial W with respect to X, dx. But this concept is coming from the tangent plane and the linearization, okay? Yeah, let's take a look at the following problem. You have a variable u, depends on another quantity, depends on x and y. So you have three variables. They are related by this equation, okay? This can be also written, okay? So you know u depends on x and y. If you don't know that, then just what is du, right? Du is some differential. Du is another is a new variable associated with u in some way in calculus. Okay, it's we call it differential of u. It's just another independent another variable associated with another variable associated with u. We have to name it, give a new name. So we put a d in front of u because somehow it's related to the derivatives. Okay. But if you know u depends on x and y, then I can write on the dependency for du dx dy. Okay, then it's partial derivative dx dy. Okay, so the partial derivative u with respect to x is going to be half of x squared plus 3y squared, and then negative 1/2. That will be 2x dx. Okay, and here, and that will be 6y dy. Okay, then you can simplify a little bit. It's going to be, and I can also simplify a little bit. It's going to be x squared plus 3y squared and dy. Okay, so you have three variables right now. You have dx, du, dy. Okay, those are the new variables. I call it differential of the variables. All right. If u, x, y are related, then that differentials must be related by this equation. Okay. So that's gradually you understand the differential. It takes time. Okay. So the dx has a meaning here. You cannot just drop it. When you look at the integral, right? Some students when you write down the integral, they do not realize this is the important part of dx. They just drop it. Usually when you write the integral, you can look at your homework. You did it. Whenever there's integral, you see, did they drop dx? Okay, and very often they just ignore that. Okay, this is a part of the important body, you know. So don't drop it. Okay, there's a reason here. It's hard to explain in 1 minute. The integral, we use the integral symbol, and then at the end there was a dx or dy. There's a reason there. Okay, it's not arbitrary put there. Okay, so yeah, so this is called differential u. Now is related to differential x and differential y by this formula. Okay. Yeah, let's just almost there. Okay, just one more problem. Okay. So you L equals x z e to the negative x squared minus z squared. Okay. So we have how many variables here? You have a x, z, and L. Okay. We only have 3 variables, but they're related. Okay. We want to find out and dl. Okay. dl depends on dx. Yeah. Find l, which depending on dx and the dz. Okay. As the idea, very simple. dl is going to be partial x dx. There's no y there. Okay, don't worry about it. Okay. So then you differentiate L with respect to x by the product rule. Okay. Minus xz e to the negative x squared minus z squared. I have to, you can put a plus here, it's negative 2x. That's dx. Okay. You have to simplify a little bit. Plus the derivative with respect to z, it's the same. So x plus xz e to the negative x squared minus z squared negative 2z, and that's dz. Okay, so let's simplify it. The first one, I can take z out. I also can take, I can also take 1 minus 2x squared and dx. Okay, and similarly, it's 1 minus 2 z squared dz. Okay. So this is dl. That's it. Yeah, we are going to understand this a little bit better. Okay, in calculus 165, yeah, I will explain this a little bit more because right now its time is over. Okay, so 165, we try to understand what is dy and how is it related to dx. Okay, if you're given a function. So that will be the topic next week. So we're next class.